Hello my dear students, welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3 hybridization with one pi bond in the structure. For that, let's take an example of phosphorus oxychloride. So today I am taking an example of phosphorus oxychloride which will show sp3 hybridization along with one pi bond in the main structure. What will be the molecular formula for the phosphorus oxychloride? It will be POCl3. Now let's make the Lewis structure of the POCl3 first before doing the hybridization. So I'm writing phosphorus over here, that's chlorine over here, chlorine, chlorine and the oxygen. Now what's the atomic number of phosphorus? It's 15. So the configuration will be 2, 8, 5. So that means phosphorus is having 5 electron in its valence shell. So I'm going to mark 5 electrons around phosphorus in the Lewis structure. That's the first electron, second electron, third, fourth and the fifth. Now let's talk about the chlorine. The atomic number of chlorine is 17. So the configuration is 2, 8, 7. That means chlorine is having 7 electron in its valence shell. So let's mark the 7 electrons around chlorine, around the all chlorines in the Lewis structure. So that's the first electron, second electron, third electron, fourth, fifth, sixth, seventh. Now let's come to the second chlorine. The first electron, second, third, fourth, fifth, sixth and the seventh. Now let's come to the third chlorine. First electron, second, third, fourth, fifth, sixth and the seventh. Now let's talk about the oxygen. What's the atomic number of oxygen? That's 8. So the configuration is 2, 6. That means oxygen is having 6 electron in its valence shell. So let's mark the 6 electrons around the oxygen in the Lewis structure. That's the first electron, second electron, third, fourth, fifth and the sixth. Now let's make the bonds in the Lewis structure. Now all the chlorines will have 1 bond with the phosphorus. So that's the first bond of first chlorine with the phosphorus. That's the second bond of second chlorine with the phosphorus. And this is the third bond of the third chlorine with the phosphorus. Now after that, oxygen. Oxygen is going to have 2 bonds with the phosphorus. So that's the first bond of oxygen with phosphorus and that's the second bond of oxygen with the phosphorus. Now let's count the number of valence electron for the chlorine after the formation of one bond with phosphorus. I'm coming to the first chlorine. The first electron, second, third, fourth, fifth, sixth, seventh and the eighth. That means first chlorine has attained the octet in its valence shell, that is 8 electrons after the formation of one bond with the phosphorus. Now let's come to the second chlorine. I'm counting the electrons, the valence electrons of chlorine, the second chlorine after the formation of one bond with phosphorus. That is the first electron, second, third, fourth, fifth, sixth, seventh and the eighth. That means second chlorine has also attained octet, the 8 electron in its valence shell after the formation of one bond with phosphorus. Now let's come to the third chlorine. I'm counting the number of valence electron for the third chlorine after the formation of one bond with phosphorus. That's the first electron, second, third, fourth, fifth, sixth, seventh and the eighth. That means third chlorine has also attained 8 electrons, that is octet, after the formation of one bond with phosphorus. Now let's count the number of electron for the oxygen after the formation of 2 bonds with phosphorus. That is the first electron, second electron, third, fourth, fifth, sixth, seventh and the eighth. That means oxygen has also attained octet, that is 8 electron in its valence shell after the formation of 2 bonds with the phosphorus. Now let's count the number of valence electron of phosphorus after the formation of 5 bonds, the 2 with oxygen and 1 bond with the 3 chlorine. So that's the first electron for phosphorus, the second, the third, fourth, fifth, sixth, seventh, eighth, ninth, and a 10th. That means phosphorus has attained 10 electron in its valence shell after the formation of 5 bonds. Here, here this is the case of expansion of octet. That means phosphorus has attained more than 8 electron in its valence shell. Why is phosphorus able so? That is to have 10 electrons, the more than 8 electrons, because phosphorus is having 5 vacant 3d orbital in its valence shell. So now let's try to understand this concept in the hybridization of phosphorus in POCl3 molecule. Firstly, in POCl3 molecule, the maximum number of bonds are found by phosphorus. So here, central atom. Here central atom will be phosphorus. So let's talk about the phosphorus. What's the atomic number of phosphorus? It's 15. What will be the electronic configuration of phosphorus in terms of subshells and orbital? That will be 3s2 3p3. It's a valence shell electronic configuration. Now it's the third valence shell. In third valence shell we are also having 3d subshell, but here in this case we are not having any electron in 3d subshell. That means we are having 5 vacant orbitals of 3d subshell along with 3s and the 3p. So now let's make the orbital diagram of 3s, 3p and 3d in the form of boxes. First of all, that's the 3s subshell with 1 orbital. Now next is, this is 3p subshell with 3 degenerate orbitals. What are degenerate orbitals? The orbitals which are having equal energies. So these 3 orbitals are degenerate. These 3 orbitals are having equal energies. Now in case of 3d, in case of 3d subshell, we are having 5 vacant orbitals, or we can say 5 orbitals which are degenerate in nature. That means in 3d subshell we are having 5 degenerate orbitals, that is orbitals with equal energies. Now let's fill the electrons. The 3s is having 2 electrons, so I'm going to fill the 2 electrons in 3s. That's the first electron with a spin of plus 1 by 2, and that's the second electron with a spin of minus 1 by 2. Now let's talk about 3p. In 3p we are having 3 electrons. So I'm going to fill these 3 electrons in 3p according to the Hund's rule. And Hund's rule states that firstly, in case of degenerate orbitals, all the orbitals will get 1 electron each. After that the pairing will start. So that's the first electron, second electron and the third electron. So we have filled all the available electrons in the valence shell, and that's called ground state. That's called ground state. Now let's come to the Lewis structure. In Lewis structure, phosphorus is forming total of 5 bonds. From here one thing is clear. If phosphorus is forming 5 bonds, that means in case of phosphorus there must be 5 orbitals which must have 1 electron each, so that the 5 orbitals of phosphorus can overlap with the orbitals of chlorines and the oxygen containing 1 electron for the formation of covalent bond. So that means here firstly we must have 5 orbitals containing 1 electron each, but right now here we are having only 3p orbitals which are having 1 electron each. So to make the 5 orbitals having 1 electron each, we must excite 1 electron from 3s to the 3d orbital. So here 1 electron has been excited or jumped from 3s orbital to the 3d orbital. So let's make the excited state. So firstly, this is the 3s orbital. These 3 are 3p degenerate orbitals, and these 5 are 3d degenerate orbitals. Now here the 1 electron has been jumped from 3s to the 3d. So 3s is left with only 1 electron. 3 electrons were in the 3p and the excited electron from 3s has entered the 3d orbital. So that's called the excited state. Now let's come back again to the Lewis structure. Now here I'm mentioning one thing. Whenever there is a formation of two bonds, whenever there is a formation of two bonds between two atoms, in this case we are having two bonds between the oxygen and the phosphorus. In case of two bonds, one bond is always sigma and the another bond is always pi. So that means here, if phosphorus have formed 5 bonds, out of which 4 bonds will be the sigma and 1 bond will be the pi. Now the rest of the 3 sigma bonds are the bond of phosphorus and chlorine, and the phosphorus and chlorine. We got the total of 4 sigma bonds and the 1 pi bond. So now in the next step we have to talk about the hybridization. Before doing hybridization, let me mark one point again, that hybrid orbitals only forms sigma bonds but not the pi bonds. Hybrid orbitals only form sigma bonds, and here how many sigma bonds are forming? It's 4. So that means in hybridization we need to mix only 4 orbitals, not all the 5. So here we need to mix the 4 orbitals. So that 4 orbitals will be the 1 orbital of the 3s and 3 orbitals from the 3p. So 1 s orbital and 3 p orbitals will intermix Why I have taken only 4 orbitals, the 1s and 3p? Because in the Lewis structure we found that only 4 sigma bonds were forming, one was the pi bond. So for the formation of 4 sigma bonds, the hybridization must involve only 4 atomic orbitals. So that means 1s and 3p orbitals will intermix, so that we will get the 4 hybrid orbitals, and that 4 hybrid orbitals will form the 4 sigma bonds. Hybridization or hybrid orbitals does not form the pi bonds. So that means here we got the 1s and 3p in intermixing or the hybridization. So the intermixing of atomic orbitals, the 1s and 3p, is called hybridization. After that, here we have mixed 1s and 3p. Total of 4 atomic orbitals are intermixing. So we will get 4 new hybrid orbitals. The number of hybrid orbitals obtained will always be equal to the number of the atomic orbitals mixing. Here total of 4 orbitals, the 1s and 3p orbitals were intermixing. So we got the 4 new hybrid orbitals, and one thing more, that hybrid orbitals will again degenerate orbitals. That means the energy of all the 4 hybrid orbitals will be equal. So we got total of 4 new hybrid orbitals and degenerate orbitals. So these are the 4 new hybrid orbitals. Now, what will be the name of these hybrid orbitals? Now 1s and 3p are mixing. That means the name of first hybrid orbital will be s and the p 3, because 1s and 3p has intermixed to form this new hybrid orbital. So the name of other 3 hybrid orbitals will also be sp3. The third hybrid orbital will be sp3, and the fourth will be again sp3. And sp3 signifies that we will be having 25% s character and 75% p character and 75% p character per hybrid orbital. Now, what we are left with? We are left with a 3D orbital which was having one electron. So we need to make that 3D subshell again along with the sp3 hybrid orbitals. That's the 3D subshell. So now let's fill the electrons. The one electron was in 3s and 3 electrons were in 3p. That means we have to fill total of 4 electrons in sp3 hybrid orbitals. So we will fill that 4 electrons according to the Hund's rule. So firstly, all the orbitals will get 1 electron each. If there is availability of electron, after that there will be pairing will start. Now 1 electron was in 3D, so we are filling 1 electron in 3D over here. Now what next? Now let's talk about the chlorine. Now I'm talking about chlorine. Chlorine. What's the atomic number of chlorine? That's 17. So its configuration will be, the valence electronic configuration will be 3s to 3p5. So we need to draw the 3p subshell. 3p subshell will have 3 degenerate orbitals, we know that. Now, how many electrons are there in 3p? They are total 5 in number. So 1, 2, 3, 4 and 5. So in 3p subshell we are having 3 orbitals in which we have filled the 5 electron, and you can easily see that we are left with one of the 3p orbital with 1 electron, which will overlap with the sp3 hybrid orbital of the phosphorus. Let's come over here. Let's talk about the first chlorine. That's the 3p subshell of first chlorine. How many electrons were there in 3p? There were 5. 1, 2, 3, 4 and the 5. So that means there is one 3p orbital which is having 1 electron in case of chlorine, which will have the head-on overlap with the sp3 hybrid orbital of the phosphorus to form the sigma bond. So we got the first sigma bond that has been formed between by the head-on overlap of sp3 hybrid orbital of phosphorus with the p orbital of the chlorine. So we got the first sigma bond. Now let's talk about the second chlorine. I am making the 3p subshell of second chlorine. That's of second chlorine. In total we were having the 3 chlorines. And now in chlorine we are having 5 electrons in 3p subshell. So that's first, second, third, fourth, fifth. Here also we are left with one of the 3p orbital which is having 1 electron. One of the 3p orbital which is having 1 electron, which will have the head-on overlap with the one of the sp3 hybrid orbital of phosphorus to form the sigma bond. So we got the second sigma bond, which is termed as sigma sp3p, because it has been formed by head-on overlap of sp3 hybrid orbital of phosphorus with the p orbital of second chlorine. Now let's talk about the third chlorine. Now I'm talking about the third chlorine. I'm drawing the 3p subshell of third chlorine. That's 3p of third chlorine. Now again 3p is having total of 5 electrons. The first, the second, the third, fourth and the fifth. Here also we are left with one of the 3p orbital with 1 electron, which will have the head-on overlap with the one of the sp3 hybrid orbital of phosphorus to form the sigma bond. So by this way we got the third sigma bond of type sigma sp3p because it has been found by head-on overlap of sp3 hybrid orbital of phosphorus with the p orbital of the chlorine. Now, here we have completed about the chlorine work. Now let's talk about the oxygen. Now I'm talking about oxygen. What's the atomic number of oxygen? It's 8. What will be the valence electronic configuration in terms of subshell? That will be 2s2, 2p4. That means we have to firstly draw the 3 orbitals of 2p. We got the 3 orbitals of 2p, and here we are having 4 electrons in 2p. So that first, second, third and fourth. This is the Hund's rule, that firstly all the electrons of firstly all the degenerate orbitals will get 1 electron each. After that pairing will start. Now let's make the bonds of oxygen with the phosphorus. Here let's talk about the oxygen now. I'm talking about oxygen. In case of oxygen, I'm making 2p orbital. That's our 2p orbital. And in 2p we were having total of 4 electrons. So let's fill them. That's first electron, second electron, third electron and the fourth electron. Now here we are having 2 orbitals in 2p of oxygen which is having 1 electron each. That will form the bonds with the orbitals of the phosphorus. So the first 2p orbital having 1 electron will form the sigma bond with sp3 hybrid orbital of phosphorus by head-on overlap. So here we got the fourth sigma bond that has been formed between or by the overlap of head-on overlap of sp3 hybrid orbital of phosphorus with the p orbital of oxygen. So we got the fourth sigma bond. Now what next we are left? Here now we are left with the another 2p orbital of oxygen which is having 1 electron, which will have the lateral or the side overlap with the electron present in the 3d orbital of the phosphorus, thereby forming the pi bond. So this is the pi bond that has been found by sidewise or lateral overlap of 3d orbital of phosphorus with the 2p orbital of the oxygen. The pi bond has been formed by sidewise or the lateral overlap, and this pi bond has been formed between the p orbital of oxygen and the d orbital of phosphorus. Hence it will also be named as p pi d pi bond. So that's all about the hybridization, and here I have shown you that all the sp3 hybrid orbitals, we are having in total of 4 sp3 hybrid orbitals, and all of them has formed the sigma bond. The electron which was left in 3d orbital has formed the pi bond with the 2p orbital of oxygen by the sidewise or the lateral overlapping. Now let's come to the structure. Here we got the sp3 hybridization. sp3 hybridization. In sp3 hybridization, the geometry will be tetrahedral. Now let's make the geometry. That's the phosphorus. We got the double bond O over here and one chlorine over here. So these two bonds are on the screen. This is called wedge bond, which is coming out of the screen, and here we have placed the chlorine. So this wedge bond is coming out of the screen, sorry. This wedge bond is coming out of the screen, and we have placed a chlorine over there, and we got the dash bond. This dash bond is going inside the screen, and here I have also again put down over there chlorine. So that's the geometry of the POCl3. Now I'm deleting this wedge and dash. I hope you got understood, because I have to tell you one more concept. Now let's take this angle to be theta 1 and this angle to be theta 2. We know that normal tetrahedral angle is 109 degrees and 28 minutes. But in this case, theta 1 is greater than 109 degrees and 28 minutes. But theta 2 is smaller than or lesser than 109 degrees and 28 minutes. I'm repeating it again. Let me write it again. What is a normal tetrahedral angle? It's 109 degrees and 28 minutes. Here the theta 1 angle, the value of theta 1 angle is greater than 109 degrees and 28 minutes, and on the another hand we are having the angle theta 2 whose value is lesser than 109 degrees and 28 minutes. So here angle is disturbed in case of tetrahedral geometry. So we will name this structure to be distorted tetrahedral. So the name of geometry of POCl3 will be the distorted tetrahedral. So why these angles are getting varied in the structure, we will discuss about this thing in the VSEPR theory. The valence electron pair repulsion theory will answer why there is a variation of angles in case of POCl3 or the geometries which are having the lone pairs. Now I'm left with one of the point, that's the energy point, which I always mention at the last. Here in this whole process there are two endothermic steps. The first one is the promotion of electron from 3s to the 3d. So here I am writing, here is consumption. Here is consumption of energy for the promotion of electron from 3s to 3d. This energy which is getting consumed is also called promotional energy. That's also called promotional energy. So in this case, at this step actually, there is a consumption of energy for the promotion of electron from 3s to 3d, which is also termed as promotional energy. Now the second step, which is endothermic, it is the intermixing of atomic orbitals. So is the consumption of energy called hybridization energy. Here is the consumption of hybridization energy for the intermixing of atomic orbitals to get the new hybrid orbitals. Here is the consumption of hybridization energy. Now we got the two steps where energy is getting consumed. Now let's come to the last step. Here is the formation of the 4 sigma bonds and the 1 pi bonds, and the formation of new bond is always exothermic in nature. Here I am writing, during the formation of 4 sigma bonds and 1 pi bond, comma, there is release of energy. There is release of energy which compensates or recovers, the promotional energy, and hybridization energy. As both of these energies are getting compensated during the formation of 4 new sigma bonds and the 1 pi bond, That's why the formation of POCl3 is feasible or practically possible. I'm repeating it again, that the two endothermic processes or the two steps where energy is getting consumed is the promotional energy and the hybridization energy, which gets compensated during the formation of 4 new sigma bonds and 1 new pi bond. That's why the formation of POCl3 is practically possible or feasible. So that's all about the hybridization of phosphorus in case of phosphorus oxychloride. And in the structure, we got the 4 sigma bonds and 1 pi bond. Let me mark the bonds also in the main structure. We got the 4 sigma bonds. The bonds are sigma sp3p, sigma sp3p, here also sigma sp3p, this is also sigma sp3p, and we got 1 pi bond, which is p pi d pi bond. So that's all about the hybridization of phosphorus in phosphorus oxychloride, in which there is a formation of 4 sigma bonds of same type and 1 pi bond, that's p pi d pi. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.